of our last couple of classes, that is, we have started discussing about counting technique, and for the last couple of classes, we are discussing about different counting techniques. So far, we started with the concept of rule of sum and rule of product regarding counting, and sometimes we have to multiply, sometimes we have to add during the time of counting. And then we discussed about that is PG and whole principle. It's separately a different counting techniques. In some specific cases, we can apply that one. And then we discuss certain, not discuss actually, there is a known thing. There is concept of permutation and combination. That is the thing, maximum time as a counting technique we have to use in different applications. And today we are having again another approach, again that is known to us in class 12 level. We have done that is binomial expansion, and that is also a part of counting technique. That's why we are having this topic here in this module 3, where combinatorics is the chapter heading. And this combinatorics, it is having certain other approaches. Certain other approaches means next class actually we see will see those things, that is generalized concept of permutation and combination. So today we will discuss basically the binomial expansion corresponding approaches, which is a part of counting technique, and we will try to identify how this binomial expansion or this binomial coefficient helps us during the time of counting. And then we will discuss certain specific cases regarding permutation and combination. Again, these are the things, known things, that is say these permutation and combinations, certain specific situations are quite possible when we are trying to count a thing which is repetitively present there. So that repetitive approach we can apply in case of permutation, that repetitive approach in case of combinations we can apply as well. So that's why those two specific cases, because these two are very important with respect to permutation and combination, we will check. And then finally we will discuss about a certain situation whenever we will try to count an object which is distinguishable, it may happen, and which is indistinguishable, it may happen. So that's why there is a concept of distinguishable object and indistinguishable object. Whenever we count, that time approaches, it becomes different. So those things basically we will try to focus at the end of this class. So let's start the class with this concept of binomial coefficient. And this particular binomial coefficient, actually already we have approached that in our previous class whenever we discussed about the concept of combination, that is NCR, choose R element out of N element. So this expansion, how it helps during the time of counting, if we try to focus, then basically our approach is that these are the things we will discuss in today's class. And I have shared this particular PDF in the Telegram group as a reference. You can use that one. And these PDF, actually it's a PDF version of our the book Rosen. Fine. So whatever is there in the Rosen, it's a gist present with respect to the chapter 6, that is the counting technique by combinator chapter summary is present here in these slides. So I must request all of you that just because counting technique is a very important, and not only theoretically, but instead of theory, we have to habituate ourselves with respect to the problem statement wise. That is, we have to perform certain sums. So that's why more and more we try to habituate ourselves with certain problems of permutation, certain problems of PG and whole principle, certain problems of full abstraction, that is what is the name, principle of inclusion and exclusion. That is also counting technique we have seen. That means that is the nothing but A union B equals to A plus B minus A intersection B. So that's in A intersection we subtract, that's why it is known as rule of subtraction. So based on these different approaches, we not habituate ourselves with different types of problem. Ultimately we'll face problem, because in the semester exam it is expected that instead of theory from these portions, it is expected more and more sums will be there. And these sums, I think that you have also seen, because you are doing the pre-placement classes most probably. These are the part of that aptitude, this permutation, combination kind of approaches. These are very much part of this pre-placement activities, and especially aptitude portion. So that's why due to that also we have to the concept clear and have to solve more and more problem, so that will be a help during the final hours. Now start with this concept of binomial theorem. We must focus at the basic of this approach at first. So it is saying that once we are having certain variables, variables something like x, so we are having this type of variable x and y, and we are trying to add them. Clearly, it is a plus sign there. So we are.
Excuse me, sir.
Sir, your
Yes.
voice is cracking.
Sir, your voice is cracking, sir. It's not
Okay.
clear, sir.
Okay, right now, is it okay?
Yes, sir. Now clear.
Yes, sir.
Okay, okay. Okay, so this expression is the sum of two terms. A binomial expression, it's a
Sir,
sum
can you
of two
please
terms.
repeat from the start?
Actually, in the start, I mentioned that regarding this combinatorics chapter, instead of the theory, it is very much important to practice more and more sums. So that's why I suggested that you better follow the Rosen corresponding exercise book, Rosen corresponding exercise. So lots of problems are there, as well as throughout the chapter many problems it has been solved there. So you also can go with that one. So unless and until we are doing more and more sum based on different counting approaches, like some of the problem based on Pigeon hole principle, some of the problem based on principle of inclusion exclusion, unless and until we are doing that, we will not be habituate ourselves with that concept that what exactly the problem is given to us, then which counting I would apply. Is it principle I have to apply? Is it combination of is it
No, sir. Your voice is again cracking, sir.
My voice is creating problem. Okay.
Sir, maybe there is network issue.
Okay. Am I clear right now?
No, sir.
Sir,
No,
your
still
voice
cracking,
is
sir.
cracking.
Same.
So now what is the situation? Clear?
We can't hear you clearly, sir.
So it is still cracking.
Sir, your voice is cracking.
Going on there. Okay, so right now, is it fine right now?
Yes, sir.
Yes, sir.
Okay. So that's the first instruction I gave to you. That is try to solve more and more problem from that was it. As well as I will share a PDF available to me right now. That is the book I also refer in the class, the book of Chandrasekhar and Uma Parvati. That is a book also, lots of problems are there, and I must request you that a selective portions of the book as a PDF, it's a scanned version of the book. it is ready to me and available to me, I will post that in the Telegram group. So you also or you can also follow that one. Fine. So it is also having more and more collection of that problem, because as you can remember that during the time of propositions and predicates, different types of problems are there. So in this book of Chandrasekhar and Uma Parvati, lots of solved problems are there, as well as chapter wise problems, exercises are there. So that will be a help to all of us. Fine. As you have seen, most probably that is the midterm one. It will be started most probably from 5th of October. So we have to prepare accordingly. Fine. So problems we can expect during the time of midterm from each and every chapter. So that's why. So try to practice these problems. Fine. So am I clear right now? Is it audible clearly?
Yes, sir.
Yes, sir.
Sir,
Okay. Okay.
sir, what would be the syllabus of midterm one, sir?
I was thinking that actually total 4 chapters are there, and already 2 chapters we have covered, and third chapter it is combinatorics going on, and fourth chapter certain concepts of graphs are there. So I was thinking that up to the third chapter, most probably it will be completed within this month of September, and already the counting technique, different counting techniques we have discussed, and I think that one more class I will take to complete this counting portions or combinatorial portions, and that's why after that the counting corresponding another portion is there, combinatory corresponding another portion is there, that is advanced counting technique, where the topic is basically recurrence relation corresponding. There are certain counting techniques, if again and again we have to count repetitively. In that case, different approaches are there. So that is the recursive approach. So that is advanced counting technique we say. So up to that, that is up to module 3, that should be the syllabus. So starting from propositions and predicates, then the set relation functions corresponding thing we have done in the module 2, and then finally module 3 combinatorics. These 3. Okay, is that clear? Or any issue it will be? What do you think?
No, sir, clear, sir.
Fine. So up to that, then the module 2, midterm 2, there we try to cover that graph theory corresponding thing. But this is the very important portion, that is the combinatorics portion. That's why I was thinking to include that in the module midterm 1, so that you will practice more and more. Fine. And as a suggestion, if I ask you that in the midterm questions, what type of questions you will expect? That is more and more sums or theory? Which one would be better for you? Your suggestion? Sums.
Sir, theory
Okay.
and some
The
mix.
theory would be, sir.
The theory would be better, sir.
Sir, theory would be, sir, theory would be better.
Okay, but if you said
80% theory, 20.
Sir,
But-
some will be easy to solve. Not very much time consuming.
Yes, sir, that's
Okay.
because
We can
of
solve fast.
Absolutely.
Theory we have to write for a long time.
Sir,
Okay.
Sir, everybody has a different.
even we
Absolutely. That's why I'm taking
Sir,
feedback from you.
just give us in a mixed form, theory and some in equal ratio.
Mm,
Yes, sir,
absolutely.
that would be, sir, better option, sir.
Okay, actually the pattern most probably you have noticed that either in the midterm or in the semester, we are following one pattern this time. If it is online, then only. So as last meeting it was discussed that most probably it would be tried at first, that is on offline mode. That means we are expecting that from 1st October onwards, if instructions from governments are there, that is we can open that institute, so then it would be a offline mode exam. And if it's a offline mode exam, so there is no issues. But if it's online mode exam, so pattern is most probably you have noticed that a question it is having 2 parts, A, B, and it contains by carries each. So total 10 pairs of questions it is expected. That's the pattern we follow. So that is different from our conventional 2, 5, 15 marks question. Fine. So that way actually we are habituated. So if we follow that pattern of 7 plus 7, so exactly my intention, but my suggestion, it will be definitely a mix of theory plus sum, definitely. But the problem of theory is that theory, if we give more and more, then just because it's a online mode, if it is, then just theory, it can be handled in a different manner. But if it is a sum, then you have to perform that individually. So that's the approach is always possible. So that's why it will be mix of definitely sum as well as theory. Fine. So that's why I was asking that you must practice from these two books, Rosen and as well as Chandrasekharan. Fine. Now, let's start today's class. Quickly wrap up these things. These are the known things. That's why I hope I will take less amount of time today. So, the binomial expansion, it's a sum of the expansion of an expression, and that expression, it can have either variable or a constant. Something like here you can notice that is written x plus y, and here x and y, two variables are there. So this is an expression, x plus y. And what this expression suggests? This expression suggests I require a combination of x and y both. So this way it is suggesting. Now, if it happens that these expressions more and more we are having, that is x plus y, three expressions of x plus y we are multiplying. So that indicates that we will have an expression that is x plus y whole cube. So if we expand this expression, individual terms we can identify. So what is the significance of those individual terms? Like x plus y whole cube, all we know that x cube plus thrice x square y plus thrice xy square plus y cube. But these individual terms, that is x cube by x square y by xy square by y cube, that represents actually a combination of certain element. So combination of certain element means what? Now 2x and 1y, that is x square y. If we combine, how many combinations of x square y we can frame out of this x and y? Say if I consider that x is a chocolate of category Cadbury and y is a chocolate of category Star, then how many combinations of two Cadbury and one 5-star is possible? So from that x square y corresponding coefficient, we can identify that count. So that is the approach we can apply in case of binomial expansion. So binomial expression is a expansion of the term. X plus y whole cube. This is the expression we are expanding, and that way we are saying that we are framing this equation x cube plus x square y plus xy square plus y cube. Now the important thing is the coefficient portion. Which one is coefficient? Now x cube coefficient is 1, x square y coefficient is 3. We know these things, and xy square coefficient is 3. So that coefficient, that is the coefficient portion we are denoting, that is helpful during the time of counting. So we'll check that thing. But this is a specific expansion we have done, x plus y whole cube. Now its generalized expansion, that is x plus y whole to the power n, that is the important notation we will follow, because that a generalized notation every time we can use whatever count we have to perform. So that generalized expression, if we check, then we can notice that is this expression x plus y whole to the power n, it's a summation of n j, that is n cj, that is choose j element out of n element, and x to the power n minus j, y to the power j. So that is the j0 to n summation of this expression, that is the binomial expansion of this x plus y whole to the power n. Please somebody mute yourself, lots of noise are coming.
Sir, someone mute you.
Sir, somebody has muted you, sir.
Yes. Is it audible right now?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So, this expression or this expansion of x plus y whole to the power n, we are getting that the coefficient of x to the power n, it is coming starting from j0, that is nc0. Similarly, nc1 x to the power n minus j, that is n minus 1 y to the power 1. This way we are having that expansion. But the important fact is, just because we are discussing about combinatorics, so the count of the elements, that means count of, as I mentioned, that how many count of x to the power n minus 1 and y, it is there. So our answer should be, it's a n choose 1. That is the answer. So whenever we are counting, if it happens that in the form of binomial expansion we can convert it, then we can easily identify this coefficient from that expansion, and we can say that this is the total count. So that is the reason we are discussing about binomial theorem during this time of combinatorics. Now, if we see this particular problem, then that will clear our point of view. So it is asking that what is the coefficient of x to the power 12 and y to the power. So actually, if I say answering approach is quite clear, I hope, because we have applied that binomial expansion formula, that is ncj and x to the power n minus j. So here x is 2x to the power n, that is 25 minus j, and y to the power y is here we are assuming minus 3y, the entire minus 3y term as a y to the power j. And we are trying to identify the coefficient portion only. We are not bothered about what is the value of x but what is the value of y, because we are thinking what is x per y. Now x is a category of chocolate, y is another category of chocolate, and the important fact is that x to the power 12 and y to the power 13, what is the significance of that particular thing? So it is saying that 12 Cadbury and 13 5-star you want to choose. How many ways we can choose? So now the issue is, whatever coefficient we are identifying from these expressions, that would be the approach. So right now it is asking that what is the coefficient of x to the power 12, y to the power 13, and using the generalized approach of the formula we have identified that one. So that coefficient we can utilize during the time of counting. That is the approach of binomial coefficient during the time of counting we can utilize. Now, if that is clear, then certain little bit what I can say, there is a corollary concepts we can identify from the binomial expansion, that it is talking about that whenever we are trying to identify coefficient, look carefully how it is happening. Now we are saying that first we will identify nc0, then nc1, nc2. These are the coefficient thing I am talking about, not the x by y corresponding portions. So only the coefficient portion, if you notice, then you can notice that is as it is also mentioned, summation of k0, that is the j thing, 0 to n. So nc0, nc1, nc2, these are the coefficient thing, and it says what actually? It says that out of n element, how many ways I can choose? 0 element, isn't it? Out of next coefficient, out of n elements, how many ways I can choose? 1 element. Out of n element, how many ways I can choose? 2 elements. Something like that way it goes on. So that it is saying that once we are saying 0 element, 1 element, 2 element, these are nothing but a subset of elements. So our total set length is n, and this j by k, right now it is k here in the slide, it is mentioning k. So this k is nothing but cardinality of subset. That is how many ways we can select k subset, or that is the k length subset out of the set cardinality n, or the set length n. So it is talking about, that is in CK, where K 0 to N, that is all the possible number of subsets. As we have noticed that if we are having a set A with the length N, how many possible subsets are there? And the answer is 2 to the power N. So exactly that is why it is also saying that is summation of K0 to N NK, that is NCK, is equals to 2 to the power N. So that is nothing but number of subsets. 2 to the power N also denotes in case of set, that is a set length N, then number of subset possible 2 to the power N. So here the binomial coefficient is also saying all the coefficient, if we sum, that indicates that all the possible subsets actually we are identifying. So that is also equals to 2 to the power N. So number of subset choose and the binomial coefficient, all the combinations of all the accumulation of coefficients, that is same. Now,
Sir, what is K here, sir?
what is K?
K, sir.
K is the length of the subset. That is, initially we are saying K0, then K1, NC0, NC1. Look at the coefficient portion of the binomial expansion. That is the K. NC0 means that is the K portion. K is 0. Here NC1, that is the K is 1. So number of subsets we are choosing out of the set whose length is n. So that is the K thing we are discussing here. That is the K. Now from these concepts of binomial expansion, we can generate a Pascal tree, or the Pascal formation based on the formula of this Pascal identity. We can generate a Pascal tree. So the formula is something like that: n plus 1k. What exactly it is? Now, out of n plus 1 element present in a set, we want to choose k number of subsets, something like that. So that actually is saying n ck minus 1 plus n ck. So the Pascal triangle, if we frame from this Pascal identity, that actually form a triangle something like this. And this time, if I say that, look at this third column, a third row of this Pascal triangle, where the formula is that n plus 1 ck equals to n ck minus 1 plus n c, if I go back, n ck. That is the formula of Pascal identity. So for using this particular formation or formula, we have framed this particular Pascal triangle, and look carefully what it is saying: 1 3 3 1. That is nothing but the coefficient present in case of x plus y whole to the power cube. X plus y whole to the power cube. What is that? X's cube, coefficient is 1, plus 3x square y, coefficient is 3. Then 3xy square, the coefficient is 3, and then y cube, the coefficient is 1. So 1 3 3 1, these are the coefficient present in case of x plus y whole cube, corresponding expression. Fine. So exactly based on this concept, if you notice that something is happening here, what is exactly the Pascal identity, the rule that is quite present? Look it carefully. Now first, the adjacent one is generating the next row corresponding value. What exactly it is talking about? 1 plus 3, that is generating this 4. That is generating this 4. Next, again the adjacent one, that is the 3 plus 3, that is generating the next, that is 6. Next, 3 plus 1, the next adjacent, 3 plus 1, that is generating the 4. And exactly that is the approach of Pascal identity. So that is what? That is n plus 1k, n plus 1 ck. The next level data you are generating based on its previous level information. And that is the reason that Pascal Pascal identity is talking about n ck plus k minus 1. That is the formation it is present here. N ck minus 1 plus n ck, that is the adjacent to term that is generating the next level corresponding term, n plus 1 ck. So this approach we use in case of Pascal triangle, and most probably this particular problem, Pascal triangle generation, you have solved during your second semester using C programming. You have implemented that one. But the nice thing is that this Pascal triangle, it helps during the time of counting. Absolutely, because it contains the coefficient, and the coefficient helps us during the way or using how many ways we can count certain combinations. X square y, that is two types of X category chocolate and one type of Y category chocolate. So that is the approach of binomial expansion we can use during the time of counting. So based on that, if we try to solve a few more problem in terms of counting, not in terms of binomial expansion, in terms of counting, that will clear our idea that how we can utilize this thing during the time of counting. So we'll go with those problems absolutely. Then we are switching to the generalized permutation and combination. Also it is mentioning generalized, but it's a specific version when we are having a situations that is repetition kind of approach is there in combination as well as in permutation. So quickly we'll go with that one. So the thing is that these are the four things we'll consider, that is repetition is present, then how to handle the permutation, how to handle the combinations, as well as concept of indistinguishable objects and distinguishable box. By indistinguishable box, so object and box, there is a combination possible in certain types of problems, so we'll check those things at the end. Now permutation with repetition, how to approach in this case. Now look it carefully, that permutation with repetition, when we go for permutation, if we have to select element or we have to count element in a ordered manner, absolutely in a ordered manner. Now you are identifying ordered and where repetition is allowed. So how many ways I can ordered in number of element initially? So but one number of element out of n initially, the first element, how many ways I can order? So n places are there, and within those n places you can put that first element anywhere. You can put the first element anywhere. So that's why how many options you are getting? N options to arrange that particular first element. Any of the n element, any of the n position you can utilize to place the first element. Now it is saying once the first element you have placed, how many remaining places are there? So n minus 1 remaining places are there. If you have placed the first element at any particular position, remaining places are n minus 1. But just because it is saying that repetition is allowed means the same place whichever you have occupied earlier, you can utilize further. So that means for the second element, once you are choosing how many ways I can arrange, actually how many options you are getting? Same n, because you can reuse the already occupied place, it is saying, the problem is saying. So that's why again the same second element, how many ways you can arrange, that is the n. So this way every element present this time you can arrange n times. So that's why how many actually elements you have to arrange? Now r element. So for each and every r element you are having options, how many? N ways you can arrange them. So that's why the concept is coming. These are the sub problem solution, that is n, and we know that sub problem solutions are available, then those must be multiplied with each other. So that's why n into n into n, how many times? R times. So the formation is coming n to the power r. So permutation with repetition, the approach is n to the power r. That is the approach. So that's why the problem as it is mentioned, that how many strings of length r can be formed from the uppercase letter of the English alphabet. So English alphabet contains 26 letters. 26 letters. So that's why the answer is coming 26 to the power r, because any of the letter you can place during the time of positioning. So that's why 26 to the power r. So permutation with repetition formula is n to the power r. Now if that is permutation with repetition, next combination with repetitions. So in case of combinations with repetitions, the formula is n plus R minus 1 CR. N plus R minus 1 CR. As we know that combination, in which case combination we can apply, that is unordered counting. If it is happening, then we can apply combinations. So in that case, the formula it is saying N plus R minus 1 CR, but N plus R minus 1 R minus 1, that is also possible. So N plus R minus 1 CR, let's check that when this kind of approach concept is required, that is combination with repetition, when unordered approach is there. So we are considering one problem when our intention is to check that is combination with repetition concept we have to apply. Now look carefully, the problem
Sir,
is,
can you please go to the previous slide once?
okay, yes. So in the previous slide we are mentioning that combination with repetition, this is the formula we will apply, N plus R minus 1 CR, which is saying how many ways we can select R out of N element. How many ways we can select R out of N element where repetition is allowed. And these are unordered selection. That's why this we are saying combination with repetition. So I'm moving forward. Fine.
Yes, sir. Yes, sir.
Okay. Now look carefully this particular problem. How many solutions does the equation x1 plus x2 plus x3 equals to 11 are there? So it can have many solutions. Fine. Like 5 plus 5 plus 1, 11. Say 5 plus 1 plus 5. So not only we have to consider 1-5 combination, many other combinations are quite allowed. How many ways we can identify values of x1, x2, x3 so that their combination becomes 11. Now, important observation is that how you can consider these particular thing as a combination problem. So is it a ordered one? That means x1, x2, x3 it must be ordered one. Always you have to follow that particular order. No, any data you are giving accordingly, that is 1, 2, 2. If you give the value of x1, x2, x3, then those values it can be jumbled up. That means with respect to different combinations of x1, x2, x3, also you can consider those same one, say 5, 5, 1. So if we can identify that is unordered approach is quite possible here, x1, x2, x3, not only that order we have to maintain, unordered approach is quite possible, then the point is that it is talking about what? Now 11 solutions are required, but in solution 11 is required. That means this problem, if I try to interpret in this way, how many ways we can select 11, that is the R. How many ways we can select 11, that is the R, number of chocolates out of these x1, x2 and x3. These are what? I can consider these as something like type of chocolate. So x1 is a type of chocolate, say Cadbury, x2 is a type of chocolate, say Park, x3 is a type of chocolate, say Eclairs. So how many ways I can select 11 chocolate out of these 3 category? Now these are category, and it is not mentioned that how many Cadburys are there, how many 5 stars are there. No, it is not mentioned that. It is only saying how many ways I can select 11 chocolate out of these 3 category. 3 is not a number of chocolate. 3 is number of category chocolate present there. So during the time, you can notice if you have to fulfill this 11 chocolate, whether you have to repeat certain type of chocolate. Answer is yes. Because if I consider one Cadbury, one 5 star, one Eclairs, I can't fulfill that 11. But total number must be 11. If we have to go in that way, one of the category repetitively I have to consider. And that's why the repetition concept is coming. Now, the concept is coming, that is it's a combination with repetition problem. When, if it happens, that is, if I try to think, if I ask you to think in this manner also, that is whenever your R is less than, your R is greater than N. Think about that way. Whenever your R, that is the number of element you are selecting, and that is greater than your total number of element, that is N. So is it possible to cover it up? No. That time we have to think that that must be with repetition. Otherwise I can't fulfill that R. So here your R is 11 and your N is 3. But 3 again is not a specific number of chocolate, 3 is category of chocolate. So that is the reason the combination with repetition formula we have applied, that is N plus R minus 1. You can notice the final expression N plus R minus 1 and CR. The last expression it is talking about, and CR. And it is going with this way, C of 13, 11 and 78 is the answer. So combination with repetition, then we have to use the formula, that is N plus R minus 1 CR. That indicates you have to choose R element out of N element, where basically R is less, R is greater than N, R is greater than N. That time the repetition concept we must apply. Now and this problem, I must say here one more thing, that is, this is a very interesting problem, because this particular problem we can solve in another approach, and we will also see that in the next class most probably. That is how to solve this type of problem, but this combination with repetition problem using another approach, that is known as polynomial approach. So that is also a counting technique. Using polynomial, how to count, we'll see that in the next class. Now I'm just keeping this because we're having problems. So that is the these are the 4 formula we have to use. Either we are having repetition or not, depending on that. So first 2 formula without repetition, and next 2 formula, as we have seen, permutation with repetition and permutation a combination with repetition. Fine. So then we are having on one important concept left, that is distinguishable and indistinguishable concept. So what exactly that is? Now right now we are saying that is 5-star, Cadbury, Eclairs, these are distinguishable. That is, each and every element I can separate easily. But if it happens that once number of same type of Eclairs, but number of Eclairs we have to choose, that is considered as indistinguishable, because those are same. So that's why this indistinguishable and distinguishable property we can apply on those elements, that is whichever element we are selecting. Not only that, but also from where we are selecting, there also we can apply these 2 property, that is indistinguishable or distinguishable. So basically a certain type of problems are quite possible based on your element you are choosing, as well as you are putting those element in which position. If I consider that is a box, then in which type of box. So based on this distinguishable and indistinguishable 2 thing, we can have a combination of 4, 2 to the power 2, that is 4. That is basically what? Now distinguishable, 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 indistinguishable, indistinguishable, distinguishable, and indistinguishable, indistinguishable. So these 4 category we can apply on that object during the time of selecting, during the time of counting. So that's why the first problem is permutation with indistinguishable object. So indistinguishable objects, whenever it is saying, look, go with the problem, let's go with the problem. I hope that will clear our idea. The problem is saying that is how many different strings can be made by reordering letters of the word. These are the very common aptitude questions basically. During the time of pre-placement, most probably you have seen these problems. So this time, how many indistinguishable objects are there, you can categorize them, and that exactly it has been done here. So how many elements are letters are there, that is unique letters, S, U, C, E, S. SUCE 4, and some of the letters repetitions are there. So in this case, whenever this type of problem is there, so this is a permutation with indistinguishable objects. Whenever it is saying a formula we can apply, and this exactly the formula, that is total number of total number of count, that is n factorial, divide by your distinguishable object corresponding count. So in one, it may happen certain type of object, and how many times it is there in one time, like S 3 times. We have seen S 3 times it is present. So S count it is happening here 3 factorial. So that is why 3 factorial we have divided by 3 factorial, and total count is 7 factorial, that is total number of letters present here. So in case of permutation with distinguishable objects, the formula it is saying n factorial divided by individual objects which are actually distinguishable and their count. So in 1 factorial, n2 factorial, nk factorial, where we are saying k number of objects we are having, and individually they are having a count of n1, n2, nk, something like that. So in case of permutation with indistinguishable object, this particular formula we can use, and we will see that these are very quite common problem in case of combinatorics. Now this distinguishable and indistinguishable property, as I was saying, that we can apply this on the objects and the box. Basically, what is object, what is the concept of box is coming certainly. So concept is that we have to select number of objects and we have to put those objects in certain box. That is the objective. So objective is select number of objects and put that into a box. So during the time of selecting objects, it may happen that objects are distinguishable and objects are indistinguishable. And in case of boxes also, where you will place those objects, it can be distinguishable boxes, that is separate boxes, or it can be indistinguishable boxes. It is anywhere you can put. So that's why these distinguishable, indistinguishable object box creates makes 4 type of situation, and out of those 4 type of situation, 2 specific situations we can handle using 2 definite formula. One is already we have seen, that is permutation with indistinguishable objects. So where it is saying that is distribute indistinguishable objects in number of distinguishable objects into k distinguishable box. If that way it is there in the problem, then the formula we can apply, that is n factorial divided by n1 factorial, n2 factorial, dot 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 k nk factorial, where k number of distinguishable boxes are there. So that is one formula. Another formula is there, that is how many ways we can place our indistinguishable objects into indistinguishable boxes. Fine. So in this short span of time, it is not possible to exactly point out, that is what kind of property with respect to distinguishable and indistinguishable concept is going on. So that's why it is very much required to solve certain type of problem based on these properties. Fine. So I must request that from the Rosen, try to go with this chapter and try to practice certain problem based on these distinguishable objects, as well as distinguishable boxes, as well as indistinguishable objects and indistinguishable boxes. So we are having 2 specific formula based on this distinguishable object and distinguishable box, as well as indistinguishable object and distinguishable box. In other 2 cases, there are no such specific formula. So in that case, we have to utilize the concepts logically. We have to think during the time of counting. So today is that much. So try to solve certain problem based on these concepts from the Rosen exercise. And if you face any problem, let me know. Fine. So today is that much. Next class will, as I mentioned, that is how to solve certain counting technique using polynomial. We will check. So if you are having any query right now, you can place. Otherwise, I must give you the attendance link quickly. Okay. Yes.
So can you give some example for distribution objects into boxes?
Exactly. That's why I mentioned that is please go and check the Rosen because right now it is not possible. Time is not there. If
Sir, in the
you are
next
facing
class?
problem, let me know. Otherwise, I will show you in the next class.
Okay, sir. Thank you, sir.